and go to a clean plate. Here we go. All right. Let me hit, I know you weren't in here when I went over the announcements before, so I'll hit them again, also for the people who aren't here. But let me first mark that Victor was absent in the first class, and that Freddie's here for this one. The other two are not yet. Okay. Let me also get my pen set up. Okay. Well, there we go. The only announcement I have that I can think of right now is just a brief thing on office hours. Most of the time, now in the second mini term, office hours on Mondays, Wednesdays are same as they were first mini term. Monday, Wednesday, 3:15, right after this class is over with, until 5:15. Okay. Today is a minor exception. Okay. My car died last week completely, and it's in the parking lot at Pep Boys. They were working on it, and they could not get it running again. In fact, actually, what they did to it made it so it wouldn't run at all. I drove it down there, but it wasn't their fault. It was, the coolant had leaked out without giving me an indication it was leaking. It didn't give me any overheating light or anything else, and it worked. Either the head or cracked it. I don't know what it did, but when they put coolant, they repaired the hoses, put coolant in, and coolant started coming out of the spark plugs, which is not a good place for coolant to come out. So rather than, it's an old vehicle, so rather than mess with anything, we're selling it to salvage, and they're coming to pick it up at 3:45. So as soon as I get out of class, I've got to book it over the Pep Boys and get give them the keys, sign over the title to them, and get the check. And then they haul it off, and I drive my own car back here. So, and then we're in the process of getting a new vehicle. So, I will be out of the office, I know at 3:45, probably 15 minutes before and maybe a few minutes afterwards. I don't know how long it's going to take. So, hopefully no more than half an hour. So,
So you're going down there after this class?
As soon as this class is over, I book it over there, and I've got to take my plate off and wait for the tow truck to come and then sign it over.
Okay. I have some research papers. I have it with me today.
Right.
I just got to print it off.
Right.
And I was just hoping I can kind of just leave it up on your door or something.
Yeah, you can slide it under my door,
okay.
And if I'm in there, I'll take it. If I'm not in there, just slide it under my door, and I'll be back within a half hour, hopefully less than that. But, yeah, so that'll do. Okay. And other than that, as far as I know, I don't have any other issues coming up this week that I know of yet. We'll see. These things have crept up on me. Now, where did we leave off last time? We were doing in Chapter 4, which is higher order differential equations. I did give you the test on Chapter 3, right? Okay. 4.1, preliminary theory, linear equations. And we are looking at a boundary value problem that can have many solutions, one solution, or no solutions. Okay? So we're looking at the B part of this. And we had a boundary value problem in the first part of the example 3. X double prime plus 16x equals 0, and that gave us, I think, an infinite number of solutions. Okay? One unspecified parameter. But if the boundary value changes, the differential equation remains the same. X double prime plus 16x equals 0. That stayed the same, but this time your boundary value is x of 0 is equal to 0, which is exactly like it was before. But then this time we're having x of pi eighths, not pi halves, equal to 0. The last time it was x of pi halves equals 0. Okay? So this time it's x of 0 equals 0, same as before. The equation, differential equation is the same, but now the second boundary value is x of pi eighths is equal to the same. Well, guess what? That differential equation has the same solution as we had before, which is this. X is equal to C1 cosine 4x, t. X is the dependent variable, so you need something else for independent variable. Let's call it t. This is the pain in the neck. Okay. I'm going to have to discharge and start over again. Yuck! Yuck! So sorry about this. And get my pen back and the color back. Okay. So x double prime plus 16x is equal to 0, subject to x of 0 is equal to 0, and x of pi eighths is equal to 0. Okay? Now, as we said before, x of t, I'm going to write it that way because it wasn't clear what the second variable was, independent variable was, is equal to C1 cosine 4t plus C2 sine 4t. That's the only possible solution you can have for that. You know, work it out. The first derivative would be minus 4 C1 sine 4t plus 4 C2 sine 4 cosine 4t, and the second derivative would be minus 16 C1 cosine 4t minus 16 C2 sine 4t, and then you solve that x double prime is exactly 16 plus 16 x, this thing, and that would be the only way you get 0. So that is our solution, just like it was before, but now we plug in our values. And when we plug in x of 0, what do you get? C1, because cosine of 0 is 1. Plus 0, okay. And you know that this is equal to 0. So C1 is equal to 0, okay? So now your x of t, because C1 is 0, is C2 sine 4t, right? Now we plug in x of pi eighths, and that would be C2 times what is sine of 4 times pi eighths would be pi halves, 1, okay? So that says C2 is equal to 0, okay? Guess what? We have no solution, okay? We have that x of t is equal to 0. That's the only thing that would give you those two values. Yeah.
How do you get 0?
Well, when we plug in pi eighths, we're told x of pi eighths is 0.
Oh.
So we plug in pi eighths and you get C2, and you were told that's equal to 0. C1 0, C2 0, everything 0. Okay? Here's the only function that makes that true. X equals 0. Ever. Okay? That's the only function that fits this and those two conditions. Okay? Basically, what do they say? Do they say it's a no solution or only one solution? Hence, x equals 0 is a solution and it's the only solution. Okay? So let's do C. And what I'll do for C is erase. Well, I thought I was going to erase. Okay. I probably shouldn't have erased that. Let's just start over. Okay. The x double prime plus 16x equals 0, x of 0 equals 0, and x of pi halves is equal to 1. Okay? Okay. That's our new situation there. And, of course, this is the only solution for that. Okay, just like we did before. So let's plug in our boundary values now. For some reason, there is a line going across here, which has absolutely no reason to be there. Okay, so let's plug in these boundary conditions. Well, our x of 0, we've already seen, produces C1, and C2, the sign is 0, and we're told that's equal to 0, so C1, 0. Just like before. I said I should have left that. And x of pi halves now is equal to C1, 0. So you got C2 times the sine of 4 times pi halves. Say again? Yeah. So that would be 0, okay? C2 times 0. So that is always 0, but we're told that's equal to 1. And when is 0 equal to 1? Never. Okay? It can't equal 1. So therefore we have no solution to this one. This tells us that C1, 0, and that 0 is equal to 1. Okay? And 0 can't ever be equal to 1. So this has no solution whatsoever. Okay? So, done. All right.
They said that in the other problem we just did, it said x equal to 0 is one solution.
That one and only solution, yeah. And that's just a straight line. And that's the only one you get. Now, most of the time, you'll either have initial conditions that will give you usually a better solution than that, or if you had reasonable boundary values other than the 3 they gave you, you might could have gotten one that had only one solution. But most of the time, there are going to be infinite number of solutions. That's what you expect to get, kind of, or one solution, which could be a trivial solution, or it could be only just one that fits, and that's the only one that fits, or you might actually get. So boundary value problems are not guaranteed to give you solutions. They could give you one solution, infinite number of solutions, or no solutions. It's kind of like 2 equations, 2 unknowns. You're either going to get one infinite or none. Okay. You expect to get one most of the time, but you don't always. Probably less frequently with differential equations. All right, let's go to. Goodness, my head's just started hurting. Why? Okay. Homogeneous equations. Now, remember in the last chapter, what we were calling homogeneous equations were those that had the same power in every term. Now we're going back to homogeneous equations, these equations are equal to 0. They call both of those homogeneous. You just have to make sure you understand which one they're talking about. A linear nth order differential equation, because the last time, it wasn't last section, it was the last chapter, is what I should have said. When you're talking about linear uh, uh, differential equation with multiple terms in it, and all of those have the same power, then you call that linear. Okay. But now we're talking about a linear nth order differential equation. Before it was first order. Now it's nth order differential equation of this form. This is your good old standard form, a sub n of x. Now that n there is just a marker that tells you this is the coefficient function that goes with this derivative, dny dx to the n. Okay? That's just saying this is the coefficient function that goes with that derivative. Okay? Plus a sub n minus 1 of x d n minus 1 y over dx to the n minus 1. Now, I like to put those in parentheses, but they don't, okay? Plus, I'm going to leave off the rest of them. I usually like to do at least 3, but I just don't have room. Dot, 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 plus, we'll do a couple at the end, a sub 1 of x, and again, that's just a subscript indicating that's the one that goes with the first derivative of y with respect to x, plus a sub 0 of x, and that's multiplied by y, the 0th derivative of y, and that's equal to some g of x. Now that's our standard linear nth order differential equation. Linear because this a sub x has no y dependence at all. There are no other derivatives multiplied by the nth derivative or any of the other derivatives. The coefficients are only functions of x, so the only place you see a y here is in the nth derivative, the n minus first derivative, the n minus second, down to the first derivative, and just y function in this. No y's over here, no y's here, except for that one, okay? No y's or other derivatives anywhere here, because each term has one and only one. And that's called a linear, that's why it's called linear, nth order differential equation, okay? These are all x's here. All the coefficients are functions of x and x alone. Okay. Now, if that g of x is equal to 0, then we call this one homogeneous. I can't write, okay? It's just ugly, 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 okay? If the g of x is not 0, it's called non-homogeneous. Okay. If the g of x is 0, homogeneous. If it's not, it's not homogeneous. If that was just 1 or 3 or 5/3, it's not homogeneous. If it's 0, is that? If it's x to the 3x squared, e to the 3x squared, that's not homogeneous. Okay. But if it's 0, strictly 0. Okay. Now, why do we say that? Well, before we get into why, let's do a couple of examples. What if you had a differential equation like this? 2y double prime minus 3y prime minus, oh wait, that's a plus 3y prime. It doesn't matter, it's just an example. Minus 5y is equal to 0. That is homogeneous, okay? Or if it was milky, call it homogeneous. No, I'm just kidding, okay. Okay, whereas x cubed, I lost it, y to the, what's that, triple prime, y triple prime plus 6y prime plus 10y is equal to e to the x. Guess what? non-homogeneous. Now, if this heated X had been up here, that would have been non-homogeneous. If the zero had been here, that would have been homogeneous. Doesn't matter what's happening here, how complicated or simple it might look, it's what's on the other side. If it's a zero, it's homogeneous. If it's not zero, it's non-homogeneous. As long as all these functions are functions of X alone. Of course, a constant is a function. Yes, sir?
Oh, hi. I'm just meant to be teaching here, I think, at 2:30.
I'm sorry?
I'm meant to be teaching here at 2:30.
Oh, I see. Okay.
Yeah. So I think this is the room.
Oh, yeah, you're right. And, well, actually, what are you teaching? The physics?
Yes.
Yeah, but it starts at 3:30.
Oh, 3:30.
Yeah. I'm sorry.
Oh, then that's fine. I just,
Yeah, because none of the students are going to be here till 3:30.
Oh, okay.
Yeah.
I'll just mind my time then.
Okay.
Definitely 3:30?
Yeah, the physics classes start at 3:30. Dr. Bryant isn't even here yet.
Oh, okay. So Dr. Lucas
Yeah.
He must have last year's schedule or something.
Yeah. Is there some place you'd like to go
Oh,
to
okay.
divide your time?
I'll be fine.
I can tell you where the library, or, I mean, any place you want to go.
I'll probably just
Okay. Well, actually, the classroom right next door, or that office is where Dr. Bryant's going to come in. You can sit there, or the office next to it, or the classroom, or anywhere you want to.
Okay.
You can go anywhere you
So
want.
let me ask you a question then.
Yeah.
So accommodating, is there anywhere I can just get access to a computer?
Yeah, that's why I was saying I know the library would be, is there any place closer to the library?
Space Center, but it's about the same.
Yeah. Yeah, probably the library. You want me to tell you how to get there?
I appreciate you. Oh, yeah, I got you.
The library has no problem with sort of when you're walking in and you move the computer.
What kind of accent? It's like, what kind of accent?
Did he have?
Yeah.
I noticed it, but I can't really place it.
Like, I feel like, I don't know.
It could have been Germanic. He's been here a long time and just has a little bit of trace of a little bit of a German accent. I don't think it was British. It could have been. Don't believe it was Irish. Possibly Scottish.
Yeah.
Maybe Scottish.
Yeah. I was kind of digging that a little bit.
Yeah. Yeah.
When we started talking, I was like, man. What's he? Do you know who he is? Or?
Yeah, he's here to teach to do a lecture in the physics class.
Oh, really? So he's a new professor here?
Huh? No, we have a grant with NASA, and the guy who's in charge of that is Larry DeLucas. I don't know if you have ever heard that name. He was a UAB professor who actually made at least one and maybe more than one trips in the space shuttle and performed some experiments in space.
Really?
And so he is in with NASA. He's no longer affiliated with UAB, or at least directly. I think he has his own company now, but he has this grant with NASA to present some classes and things here. He's bought us some fairly nice equipment and things like that. So that's a guest lecturer who he's brought in to do. And I don't know, some of them have been doing optics, and some of them are doing some other things. I'm guessing he's the one who's doing the optics. There's a certain type of optics that Lucas specializes in, Schlieren or something like that, which is a lot like goodness gracious, geometric optics. I can't tell a whole lot of difference between what they call Schlieren, or whatever they call it, optics and geometric optics. You just pretend there's no aberrations in it, and it works really nicely. So I think that's what he's here to teach. I'm not absolutely certain. Are you in the physics class that's coming up next? No, you're not.
I'm done with physics.
Okay. If you wanted to stay for the class, I'm sure they wouldn't mind having an extra body in there. Okay. All right, so these are some equations, okay? The word homogeneous in this context does not refer to coefficients that are homogeneous functions as we had in 2.5. That's what I was trying to say before. I said the previous chapter, we didn't do chapter 3, it was the previous chapter in chapter 2, section 2.5. And those, the coefficient functions, were homogeneous if they had the same power. Okay. These are homogeneous if they're equal to 0. Not the same meaning. Okay. So we'll see that to solve a non-homogeneous linear equation, as in this one with a g of x, okay, not equal to 0, you first solve the associated homogeneous equation with it equal to 0, okay? And then what we'll do is turn around and figure out what other solutions will work for the others. So we first solve for the homogeneous. So that's why we're making the distinction. So to avoid needless repetition about the remainder of this text, throughout the remainder, we shall, as a matter of course, make the following important assumptions stating the definitions and theorems of equation 1 on some common interval I, okay? The coefficient functions a sub I of x, where I is 1, 2, 3 up to n, and g of x are continuous. So all these functions, a sub n minus 1, a sub n minus 2, a sub 1, a sub 0, all those functions, and g are continuous functions. There's no discontinuities or anything else. They're all continuous functions. Okay? That's one. And, just like way back in polynomial functions, the a sub n can't be 0. Because if the a sub n was 0, this term is 0, and this wouldn't be a function, a nth order, it would be in minus first order. Okay, so we just say a sub n can't be 0. So that's the other requirement. For every x in the interval, it cannot be 0. Okay. Now, it's kind of like a timeout, and let's go to something else, okay? Let's erase all this. And in calculus, differentiation is often denoted by the capital letter D. So, dy dx, rather than writing all that, you could just write it dy. That means the derivative of y with respect to x, okay? And we call this letter D the differential operator, okay, the differential operator, because it transforms a differentiable function into some other function. It's derivative, okay? So, let's just practice on that a little bit. What do we mean by d of cosine 4x?
What do you mean by it?
Yeah.
Derivative of y
Okay.
perspective.
Okay, and there's your y, so what would that be then?
So then that would be 4 negative sine. Remember I got negative 4 sine 4x.
You got it. Okay, exactly. Okay, what would this be? D of 5x cubed minus 6x squared.
That would be 15x squared minus 12x
Okay? Now, if we say something like d, okay, now let's just look at this. This d, what that d stands for is d by dx. That operator d is exactly what capital D stands for, right? Follow that by y, you got dy dx is equal to dy, right? Now, how do we do the next derivative? Don't we do d by dx of dy dx? Whatever the next function was, we're doing a d by dx of it, right? Next derivative, okay? So that would be d2y, because you're doing d by dx times d by dx. And that would be d2y dx squared, okay? That would be the same as d2y. So you see this is a lot neater, more concise nomenclature. It means exactly the same thing, okay? So if you had the nth derivative, that would be dny, right?
Yeah.
Okay. As long as y was a function, you could take the n derivatives of it. Okay. Some functions you may not be able to do that. Okay. Now, what would you think this would mean? Wouldn't that be it?
Yeah.
Because this stands for d by dx of y plus 3 times y.
Yeah. Yeah.
So, if you have an nth order differential equation, I don't want to say all of them. I would say with constant coefficients, you can use this d notation. Now, some of these coefficients like had an x in it, well, yeah, you just put 3x in it. That would work. Okay? But you can then use these kind of notations. Okay? What would you think this meant? d2 plus 3d minus 4. Why?
I was thinking about something.
Yeah. What would this be? D?
That would be the second derivative restricted. Yeah, restricted on dx, yeah.
Y?
Well, yeah, times y. Plus, I guess, 3 times the derivative restricted. The derivative of y.
Yeah. dy dx? Yeah.
And minus 4y.
You got it. That's exactly what that means. Okay? Now, here's the ones that I was talking about before. You can have your other coefficients that have x dependence on it. Yx cubed d3 minus 6x squared d2 plus 4xd plus 9. What would that be?
That will be 5x cubed times the derivative of
Third derivative of y with respect to x cubed
minus 6x squared times the derivative of derivative squared. I didn't say that.
The second derivative.
Yeah, second derivative.
Yeah.
With respect to
X
EX
squared. Right.
And plus 4x times the derivative of y with respect to x dx plus 9y.
Okay. That's exactly right. Now, I kind of don't like that they had them being so regular in that. This could have been 9. This could have been 4x. This could have been minus 6x squared. That could, you didn't have to have those orders going down as these were going down. They made it look like you did. It could be anyway. I mean, you could have 5x cubed in front of two of those, you know, or, you know, you could skip terms. I mean, they made it look like you have to have the same order. You don't, okay? To me, that was a little wonker that they did it that way, but don't think it's a generalization, okay? Those are also differential operators. In general, we define the nth order differential operator or a polynomial operator. Now, why they introduce another letter, call it L, that means linear operator, and that's like we just saw here, a sub n of x, okay? Now that n just marks it as the coefficient function that goes with the nth derivative. It doesn't mean it has to have the same power or anything else. It's just the coefficient function that went with that. dn, okay, we treat that as a superscript, okay, plus a sub n minus 1 as a function of x, dn minus 1 plus a sub n minus 2 of x times dn minus 2 plus dot 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 down to a sub 2, we'll just call it that, of x, d2 plus a sub 1 of x, d plus a sub 0 of x, that is, that's all you need. You don't need an equal sign, just, that's it. That is your linear operator. Now, what makes it linear? There's no y's anywhere here except following the d's. And there's only, in each term, there's only one derivative of d. Okay? Only one here, only one there. No d's, no y's are there. No, the y's just follow the d's, and that's the only place you do. Here it's just dy, and here it would be times some y. The y to the first power is y, okay? It's all that can follow that, okay? You can't have a y squared, you can't have a 1 over y, you can't have anything else. It has to be y to the first power. No coefficients. Coefficients can go with a sub 0 of x, okay? As a consequence of the two basic properties of differentiation, and here they are in case you hadn't thought about them this way, d of some constant times a function of x. If you're taking derivative of a constant times a function, you can pull the constant outside. That's the constant times the derivative of that function, right? Okay, so that's one. That's when c is a scalar or a constant. C, a constant. Okay, and the second of these is that these form the linearity things. D of alpha of x plus g of x is d of alpha of x plus d of g of x. In other words, this linear operator, what makes it linear is the operating on the sum. The derivative of the sum is the sum of the derivatives. And derivative of a constant times a function is the constant times derivative of the function. Those are two fundamental properties of derivatives. Okay? Those were in your derivative laws back when they had a table of those. Those are the first two almost, always. that makes this a linear operator. If that's always true, then you got it done. Okay. The differential operator L possesses a linearity property. That's what it is. That is, the L operating on a linear combination of two differential functions is the same as the linear combination of L operating on the individual functions. Okay? Now, I don't want to erase all this. I'm only going to erase this. I should have started with a clean slate. Wasn't thinking ahead how many lines this was going to take. Because these examples we've already done for. They're examples of what we're doing, but they're not required. Whoa, don't erase that. Yuck. Erase too much. Okay. All right. These can be kind of put into one basket here. If you have L operating on alpha of x, okay, plus beta g of x. So what you're doing here, I don't know why my thing's not writing. Okay, I think I do know, in fact. What you're doing is combining these two properties into one. Rather than C, you're talking about alpha and beta, and then you're talking about the sum here. So what this is equal to is alpha L operating on alpha of x plus beta L, goodness gracious, L operating on g of x. Okay. And basically this is combining them together. If you have alpha L, this linear operator, which is any of these things here, operating on a constant times a function plus different constant times a different function, you're combining these two, constant and sums, then it's the alpha in front, L operating on L, plus beta in front, L operating on G. Okay. Where the L is this thing here. Okay. It's all pretty much nomenclature. It all pans out. Therefore, we say this L is a linear operator. It fulfills those criteria. So, that was all to give you background in this new nomenclature, the D operator, okay, which leads to the L operator, okay. Now, differential equation, any linear differential equation can be expressed in terms of the D notation. So I'm going to start from scratch here, so I won't have to erase as much later, as that takes too long. Let's just say we had a y double prime plus 5y prime plus 6y is equal to 5x minus 3. Okay? How would we write that using the D notation?
dy squared?
No, D2.
Yeah. D2.
Yeah.
Plus 5. No, plus D.
No,
plus
5. D.
Plus 6. And then parentheses times 1.
Y is equal to 5x minus 3. That's it. Okay? Because you see, the D2 is second partial with respect to x squared of y. Yeah. Plus 5 times the derivative with respect to x of y. Okay? Plus 6 times y is equal to 5x minus 3. That's it in the D notation. Okay? D2y minus 5D. Okay. They wrote a middle step in there I left out, okay? I went straight to this one. You could have written that d 2y plus 5dy plus 6y is equal to 5x minus 3. That's what they meant you to do. Maybe that's what you were planning to do. But you could just pull out that. Okay. Yeah, same thing. Okay. Now remember the L that we had before, okay? We can write a linear nth order differential equations as we had back in 6 or 7, which were the homogeneous form and the non-homogeneous form. Remember how they look? One's equal to 0 and one's not equal to 0. Okay. We can say that the L of y equals 0 would be the homogeneous form, and L of y is equal to g of x would be the non-homogeneous form. It just shortens what you have to write. You just have to define the L to be, say, this thing. If you had L being that thing, then that's exactly what you are saying there. Okay. Now, there's a theorem coming up, and we see that the sum or superposition of two or more solutions of a homogeneous linear differential equation is also a solution. Okay? So I'm going to clear stuff off the screen. Okay, 315. Okay. That guy coming in has messed up my timing altogether. Yuck. Okay. I sort of lost track of how long we had been going. Okay. Here is called the superposition principle for homogeneous equations. Let's just say that y1, y2, y3, ... up to and including y sub k are all solutions of the homogeneous nth order ordinary differential equation, dE, and this would be like that number 6, okay? I wish I could have it here. Number 6 was the homogeneous form. A sub n of x, partial, yeah. That's that thing with it equal to 0, okay? And these are all solutions to that, okay? Different solutions to that one nth order differential equation, okay? That's what's given. This implies then that the linear combination y is equal to some c1 y1 of x plus c2 y2 of x, where these are the y's that are each solutions independently, plus c3 y3 of x plus ... plus c sub n y n of x, okay? That's also a solution. It's called the superposition principle. If you know you have these k solutions of the, is that nth order or kth order? Okay. Then the linear combination of those would also be, that's where I messed up. I knew something was out of whack here. Since I only have k of these are not n of those. K, yeah, that's a k and this is a k. Because I only have k of those solutions. Okay, then that linear combination of those k solutions will also be a solution for that differential equation. Okay, that's the where your C sub i's for i's of 1 through k are arbitrary constants. They can be anything, okay? They can vary, they can change, okay? But that's also a solution on that same interval that those were defined, okay? I should have said on some interval I, okay? They are solutions on some interval I, okay? Now, they do a little proof starting with k equal 2, and then you can build on that. Now, here's some corollaries to that theorem, okay? Here's one. A constant multiple y is equal to c1 y1 of x, okay, of a solution y1 okay, y1 is one of those solutions of a homogeneous linear differential equation. It's also a solution of a homogeneous linear differential equation. The linear differential equation is also a solution. Okay, well, surely if any linear combination of a linear combination, just one of them, you know, a linear thing, okay, is also a solution. Okay, that's the A corollary. The B corollary is a homogeneous linear differential equation. Okay, always possesses the trivial solution y equals 0. Okay. Now that's not true if this is non-homogeneous. But remember, if this is homogeneous, all those terms here, a sub n x of x times this nth derivative of y with respect to x is equal to 0. You set all those x's equal to 0, all those derivatives equal to 0. Yeah, that's going to be a solution. Okay, y is equal to 0 will always work because the nth derivative of 0 is 0, the n minus first derivative of 0 is 0, the 0 is 0, you know, first derivative is 0, all those derivatives are 0, so that's guaranteed to be a solution. So you know for a homogeneous differential equation, linear homogeneous differential equation, that's always going to be a solution. There's always going to have at least one solution, the trivial, okay? But you may have many more besides that. In fact, that was usually not all that important, but you know you've got at least one. Okay, let's do example 4. All right. Here are some functions. Here's y1, and this is equal to x squared. And here's y2, that's equal to x squared log x. And it claims that they are both solutions to the homogeneous linear equation. They are both solutions of x cubed y triple prime minus 2xy prime plus 4y. Okay? On the interval 0 to infinity. Now, I can tell you one thing right now, why the interval can't start at 0. It can't include 0, because if x is equal to 0, log is not defined. That's why it can't include any negative numbers. You can't take the log of a negative number. So that gives you one reason I know you can't start before it. Now you may be able to, no guarantee, start at 0, not at 0, but beyond 0. Anything beyond 0, that's why they have the parentheses there. So that's why you don't have 0 or anything negative, because that couldn't possibly be the case. Okay. Let's just verify that real quickly, okay? What's the first derivative of y1? What's the second derivative of y1?
2.
What's the third derivative of y1? Okay? Let's do the same thing for y2. Ooh. What would that be?
You use the product.
Yes, you do. What would that give you?
I'm just going to say 2x plus.
Log x.
Yeah.
Yeah. Plus.
X squared times 1 over x.
Yeah.
Which is just.
That would just be x.
Yeah.
Right. So what would y double prime of 2?
That would be.
Okay.
That would be 2 times 1 over x.
Oh, wait, no. Product rule, just do one at a
Oh,
time.
yeah, okay, I'm sorry. I don't know what I was saying. 2 times the ln of x plus 2x. Oh, yeah.
Right?
Yeah.
Okay. That turned out just being an x, remember?
Yeah.
What's the derivative of it?
0.
Huh?
What?
1. Derivative of x is 1.
Yes.
Yeah, right?
Yeah.
Okay. So this is actually 2 log x plus 3, right? 2 plus 1 is 3.
Yeah.
I'm not pulling wool over your eye, right?
No, I think I might have.
Okay. All right, let's go back in. Okay, this one I maybe should have written it out. 2x log x plus x. That's all that's left, right?
Yes.
Okay. So then you do the first term here, derivative of the first times the second, plus the second times the derivative of the first. Right?
Yes. Okay.
Okay. So that gave you 2, and then derivative of this is 1.
Yeah.
2 plus 1 is 3. Okay? So
I was trying to figure out where we got that 2 from, huh?
let's do the third derivative of y2. Let's do of that. 2 over x. That's it. Right?
Yeah.
Okay. Now, let's see if both of these are indeed solutions. X cubed times y1 triple prime, that would be times 0, minus 2x times y prime, which would be 2, right? Plus 4y, and y is 2x. Okay? So this is 0, and this would be minus 4x That doesn't look good, does it? Oh, wait. All right, let me make sure I haven't copied something down wrong. Y1 is x squared, got it. Y2 is x squared log x, okay. They claim their solution to y cubed, or x cubed, y3 minus 2xy prime plus, oh, wait. Sorry, I was plugging in wrong. Whoa, that's the wrong one. Okay, sorry about that. We plugged in the first right, okay. X cubed times y triple prime minus 2x times y prime, which is this, 2x, right? I went up to y double prime. Yeah, y prime, sorry, okay. Plus 4 times y, y1 is x squared, okay? And this is equal to minus 4x squared plus 4x squared. Sure enough, that's equal to 0, right? All right, let's do it for y2. X cubed times 2 over x, that's x cubed times y triple prime, minus 2x times y prime. Y prime is 2x log x plus x, okay? Plus 4 times y, which is x squared log x. Okay, let's see what that adds to. This x will go into that too, so you got 2x, I'm going to write it up here, 2x squared, that's that first term, okay? And here we have minus 4x squared log x, that's the first term here, minus 2x squared, that's the second term here, right? Plus 4x squared log x, right? Well, 2x squared minus 2x squared is 0, minus 4x squared log x plus 4x squared log x, yep, sure enough, both of those are equal to 0. Okay. Okay. We didn't have to do all that, but I think it's a good practice to go back and verify what they're saying is true. Okay, you don't always have to do that, but I just wanted to remind you how to go about doing it. I shouldn't have made so many errors in it. Okay, but this is what was given to us, and we just verified both of those are solutions. Okay, and for some reason this is not erasing very well at all. In fact, it's hardly erasing at all. Would it help if I slowed down some? I'm not sure. It's so slow. Huh? Okay. All right. What they told us is these two are solutions to that differential equation on that interval 0 to infinity. Okay? What now they're saying, the superposition principle tells us that y is equal to sum c1 x squared plus c2 x squared log x is also a solution. Of that differential equation. Okay? Now, I'm not about to take its first and second and third derivatives, go back, plug in, because they're going to be the same things we just had, except they're all going to be written together. Okay? So, but sure enough, that's the case. All right? Now, Let's see if we can get this next little thing done, and we'll be through for today. The function y is equal to e to the 7th x. They claim is a solution of y double prime minus 9y prime plus 14y is equal to 0. The thought just came to me. Remember all that little side we did with the d's?
Yeah.
They're not using them. They're going back and still using these. You could have used them, but why? You know, we'll see later. We will come back and use them. But why didn't they wait till then to define them for you? I don't know. The way this book is organized, I'm trying to follow the book, but it's a bit bizarre. Okay, it says it's solution of that. Let's just see if it is. How would we check it? Y prime is equal to? You're right, e to the 7x, but times what? Times 7, right. And y double prime would be? 49 e to the 7x, right? So let's plug this in. 49 e to the 7x minus 9 times 7e to the 7x plus 14 times e to the 7x. Is that equal to 0? That's what the claim is. Well, this will be 49e to the 7x minus 63 e to the 7x plus 14e to the 7x. Is that equal to 0? Well, let's add the positives together. 49 plus 14.
Say add it again.
Yeah.
That would give you 63.
63 minus 63. That is a solution, sure enough. Okay? Now, because that's true, we know that not only is that a solution, but y is equal to any parameter c times e to the 7th x will also be a solution. Okay? And you could plug it in and go through the same thing there, and every term would just have a c in it. Okay? It's just because the coefficients without the c in it would be the same as the coefficient with the c, and they will still add a c. So sure enough, that's true. All right? For instance, y is equal to 9e to the 7th x is a solution. Okay? Y is equal to negative square root of 5e to the 7th x. That's also a solution. Okay? And so on and so forth. At least for all real numbers c. Let's leave the complex numbers out of it for a while. Probably still going to be true, but we're not going there. Okay, we'll just leave it right there. Okay, I think we've run out of time. Okay, so we'll start next time with linear dependence and linear independence. Okay, and let me mark the place here. We made sort of decent progress there. Well, it was slow. Okay, this is a long section. In 4.1, some of these I've already assigned to you to do. Do either 1 or 3 or both. Do either 5 or 7 or both. Do number 9. Do 11. Do 13. Okay. And then you can start and do some of the odds 15 to 21. Yeah, and we'll stop there and you can do the rest of them later. Okay? Good deal.
And one question. Before I turned in my research paper, I didn't have a chance to get in Blackboard because I didn't know my use of word and password. And if there was like any way, like how, what I want to know, if there's any way you want me to do the title and, or
Okay.
is anything
No,
specific?
I don't care about the title